Hello, ladies and gentlemen, and welcome back on day 4 here at the industry stage on Formnext 2024. Today it's all about artificial intelligence, and you see, it's all real. I'm still here. We had already a fantastic presentation, and there's another one to come. So, additive manufacturing, and specifically laser powder bed fusion, has revolutionized how we think about producing complex components. That was the thing that catched me the most. However, the path to perfection in this technology is still paved with challenges, especially when it comes to balancing quality, efficiency, and costs. Today, we will hear about how artificial intelligence is playing a transformative role in tackling these challenges and pushing the boundaries of what's possible with laser power bed fusion. And I'm super happy to announce the speaker for the following speech. It's Andreas Bienne. He is head of the Swiss Advanced Manufacturing Center, and he will bring us closer to the topic. Andreas, stage is yours. Enjoy.
Thank you for the introduction. I'm very glad that you still stick around and come to this short presentation on the last day of Formnext. My topic is about a digital companion that helps us understand challenges in changing from process development to complex parts. And as my previous speaker, or the previous speaker mentioned, in the meme, I try not to take an even bigger brass instrument and blow some AI stuff at you. I try to explain first the problem that we afterwards solve. So please excuse if there are maybe more tables and numbers than usual, but I try to walk you through. Yeah, let's start. The challenge is, if you want to print a complex part, and you start, as also I do, and many of us do, for process development, you start with cubes and test specimens, and you try to transfer this process to a complex part, then often you wonder why it's not working. And many things you can see, others are a bit hidden deep in the data. So we take care about this today. And often, if you are not very sure, you try to increase safety margin, and you end up with a process that is not as productive as it could be. And so what goes wrong? I mean, there are many factors that can play in the difference between a test coupon and the real part. You see some are like kind of random or recurring, that are linked to how you maintain the machine, how you organize your processes. There is human error, the gas flow, everything. It's something you can understand and correct if you track your experiments, your process development. There are spatters, there is a bit of randomness. You can reduce the amount of spatters that you create by optimizing the recipe. You cannot influence where they exactly deposit if it's in a critical part. So there's some randomness that is maybe out of control. But today, we speak about the design-dependent parameters. So it's residual stress, local thermal effects, laser toolpaths, and design. So, you know, if you change the design, the laser toolpath also changes. And these effects that are related to the laser toolpath, we try to analyze a little bit more in detail now. So, where do the laser toolpaths come from? Like the laser toolpath is the instructions how the laser scans our layers. There's many influence factors, like the input parameter or the input format, the 3D model, many settings and proprietary filtering and optimization algorithms that are part of the black box of the slicer. You have thousands of layers and you have millions of vectors. If you want to analyze, then you have currently no means than just like scrolling through your files and identify manually some possible problems. So Today we will see how we can do this maybe a bit better. First, I have to include some information about another factor that brings another layer of complexity to our process. It's the response of the optomechanical system of a scanner, because there is a response to what we order from the scanner. Maybe you heard about the polygon delays. So that's the amount of time before a turn the laser starts or the scanner starts to slow down in order to keep the geometry. If there is a small offset in these settings, you can end up with overheating at the end of a vector. You can have an overshoot, and this also adds problems to your part that you are maybe not aware of, because it's the response of the scanner that is responsible for this. Why these delays are important, you see here. That's just an impeller, and you see the contour run. These small blue triangles mark the start and end of a vector. You see it's not a continuous contour. It's assembled from several vector sections. Okay, and if you add delays at the start and end, you may already see that there might be a problem. For turning, so that's now we are at the tip of the blade. We see the contour run, and yeah, I don't explain everything, but you see there are some runs that are taking a short curve. That is, if the dynamics of the scanner is not sufficient to fully scan to the edge. So you end up with a geometry error. On the other hand, you see these loops. This is a so-called skywriting. That means the laser shoots at full speed and turns quickly and comes back, and the laser is turned on again once it's over the part. There, if you are too late, too early, you have another possibility for errors. That's a layer that is in between and even makes it more difficult to interpret our errors. So there is some homework to be done. Homework that either the user or the machine integrator has to take care of, but it has to be done. And once this is done, we can start to talk about the toolpath itself. Okay, here you see you see several situations. Now I'm puzzled because it looks different here than here. So, yeah, on the left-hand column you see a skywriting path. The blue is more or less the target speed that our laser reaches. If you see a red section, there means that the laser speed is below 70% of what you ordered from the scanner. And you know that power stays the same. So you add much more energy per length unit than you should actually do. So you introduce skywriting on the left, works well. On the right, you have polygon delays that many of us use in recipes, knowingly or not. And you see if there is a polygon delay that is different from zero, you see that these sections where the speed is not met get quite long. So this can lead to an overheating and a failure of a part. Okay, now you remember the guy scrolling through the recipe manually? The question, can we do better? And yes, we can. We found a solution that actually transport our knowledge, our decades of experience into an algorithm that does the work for you, and it does it quickly. The software is called PAM. It's distributed and commercialized by Gravity Pull Systems. We have Huba Rompoli here for any questions related to the commercialization, to the product, to the licensing. Here I just want to say a few words about how it's interacting with your printing process. So it's integrating in the workflow, in the digital workflow, between the slicing and the printing. So as an input, you need your 3D file as a reference, as a geometrical reference. You need the sliced build shop file, and you need some basic information about your melt pool that you create with your laser. With these three things, we can work. And I do now some examples with you. Increasing complexity, and you see from when it starts to be really effective. So we start with a cube 10 by 10 by 10 millimeters, printed in 316L using a very well-established, well-known recipe. We have 2 contours, a hatch distance of 70 microns. We have a hatch offset from the contour of 25 micron, and we rotate the hatch by 67 degrees between layers. So we expect no porosity. On the right, you see already a preview of the analyzer that you see in PAM. Okay. For another parameter is the short vectors. Short vectors. During short vectors, the laser might have problems to reach a speed, so you try to filter out those. You detect here vectors that are shorter than 150 microns, and you see already in the cube between layers you have this you see in the blue one. As you might expect, there is either 0, 1, or 2, and not surprisingly, they are found in the corners of your cube. So very simple and very understandable. Already here, we see that there is a variation in number of vectors per layer. Also, it's no surprise, but it's notable that already in the cube you have different number of vectors per layer. Now we go one step further, and we place 20 cubes of the same kind on a platform. Different location, different angles, and some are on a higher support, so they shifted and set a little bit. Okay, so you would expect probably the same as me. So there is one table. I don't want to say a lot about it. You have a variation in the number of vectors that are scanned between the geometrically identical cubes of 1,500 vectors difference, 6 centimeters of difference in scanned total length, and surprisingly, one cube has 1 layer less. So the slicer just kind of makes the slicer output just makes the geometry 30 micron shorter, and I don't know about this before. So it's a surprise already with the cube. Now we go to a more complex part. It's a very nice pivot mechanism that is based on flexure elements, interlocked lattice flexures. And here you see a stable frame and these flexure elements that are highly critical for fatigue, for porosities that are included in the blades. Here you want the full performance that you expect. And there it's really critical what you get and that you know what you get. We place 14 of these pivot mechanisms on the platform, and we analyze them. And here we see there is some porosity detected, very low, but already the gut feeling tells me it would be good to see where they are. Are they in the frame or in the blade? In the frame, I don't care, but in the blade, yes. And yeah, here we see that's a 3D view. Yeah, you might guess that this is a cross-section of the blade, and these small red spots are predicted porosities in the blade section. Okay. It's a low, but it might be disturbing. The next geometry that we look at is a simple cube, but just added a notch of 60-degree angle, so we are always in the in-skin parameters, so we don't change to downskin or upskin parameters, but we remain in the same recipe. The hatch is now rotated by 90 degrees just to make any porosities more visible. And we vary the hatch offset. What you see here is cross-sections through this notch cube with different hatch offset. like offset of the hatching from the contour. And you see that in the down-facing part, you never find porosities, but in the up-facing part, yes. And in some, you see it in the vertical as well. PAM now predicts this. You see, there is a graph that shows the total porosity area detected or predicted from the digital file. It's not from the build job, it's predicted from the digital data. You see that this correctly predicted for 25 micron hatch offset. Here we switch to 40 micron hatch offset, and it also predicts some porosity in the vertical. You can also see it in the sketch of the toolpath data. Yes, I will skip. There's an effect that you're maybe not aware of. If you create a hatching, the slicer usually creates a hatch on the platform level. And then you add your part and you kind of cut out from the existing hatch the cross-section of your part. So now, depending on where you place your part, it might include or not one vector more or less. And indeed, the variation of the positioning of the vectors that you can get is up to 70 microns. So that's just by placing the part. So this can explain sometimes why placing a part in a different location of the build platform can lead to a different, or like that it can fail in another place if you add more of the same, exactly the same component. Now, there is a way to automatically correct, luckily. So we are not only informed, but we also know we get an assistance in correcting all these predicted porosities. There are several strategies. I don't explain them all, but you can actually, where you detect the porosity, you can add a contour, you can add additional vectors to just fix those pores before they go to the printer. Here we see different build jobs. We compare two of them. So this is still these notch cubes. In the B1, we have the detected porosities, and in B7 there was PAM applying a correction, and we redid the analysis in the same software with the same settings, and it cannot detect any porosity anymore. We can do the test in practice, so there are several correction possibilities. So an added contour, a fraction of a contour, and so on in different orders, several recipes. All were successful except for this, but there was an error that we could track that was coming from outside the algorithm. Yes, so it works. Now we apply this correction algorithm to this pivot mechanism. And you see the difference between the uncorrected and the corrected pivot in the predicted porosity is quite striking. And they carry the scale, it's different. So there might be some peaks left in the upper image or the upper analysis corrected version, but it's much lower than in the one below. You might maybe ask why there is a lot more here and a lot more here. That's just because there is more volume, more part volume. You remember there are these structural rings, and in the middle there are finer structures and basically these flexure elements. Okay, this was successful. If you look at where these corrections were applied, you see that there are quite this red. Well, so these small vectors were added, and those fixed the problem. Now this is only generated data, but you can also actually see it in reality. So you see the top two images are the uncorrected build job, And the lower two ones are exactly the same recipe, but added correction. And this, I mean, the added build time, sometimes it's a marginal addition, sometimes it's even shorter, but you drastically reduce the amount of scrap that you have out of your process. And this is truly bringing you closer to first time right if you want to go from a cube developed recipe to a complex part. I think the summary we skip, but I would like to recommend if you have any questions or even maybe data with you, take contact with Huba or visit the booth of Gravity Pool in Hall 12, booth 108A, and discuss your problems, your experience. Also challenge Huba with what you might have to say. So thank you very much for your attention and enjoy the rest of the show.
Thank you so much, Andreas, for this wonderful insight. It was highly technical, and I appreciate that, because usually we talk on it more in a general scale. So I'm not an expert, so let me nonetheless ask you one or two questions, if you don't mind. So we have seen at the very end the comparison between corrected pivot and the uncorrected one. So we couldn't see the ratio, but can you give us a figure? So how much is it better after using or integrating AI in the process?
I mean, the scale where one was like 7 times larger scale.
Yeah.
So you can just bring it down to a level that is non-critical. And now that's the beauty of this approach. Depending on how critical your application is, the tolerance for remaining porosities may vary. So you can really plan. But the thing is, it's not. I mean, everybody can live with the risk, but an informed risk management is necessary. So you know how good or how bad it is, and you can set confidence levels for the performance, and this makes it predictable, and it makes you sleep better at night, definitely.
Sleeping better, that would lead me to the customer. Yeah. How do customers perceive it? Is it something you communicate to your customers in order to say we achieved a better quality due to the integration of AI in our assurance?
Yes, I mean, sometimes we have to do some education, and not because people do not care, but this information is hidden in the machine, sometimes in proprietary formats. So you only see what you are allowed to see, and if you don't know for what you have to search, then it's hard to do all this work. So it's a long track of experience that is behind this. So we try to, first we have to explain what can be the source of the problem before we can discuss solution. That makes it hard, and that's also why I try to walk you through some of the thinking that is behind.
Yeah, that's the main topic, I think, how to approach the whole thing. So in terms of duration of the integration, how long did it take you together with Huba in order to bring it to a point where you say, now it's usable and feasible and gives us the result we wanted? What was the process behind?
I mean, it's always you have your system that you know it works, and then it's the hard work of making a product out of it is to make it work with any system. That's why we have to approach manufacturers and get access to the format so that we can interact. And this is, we have to explain that this is really an addition that is not adding just another nice tool, but it's actually solving a problem. And people understand, but it's sometimes it's not obvious.
Yeah, Very good. Andreas, thank you so much for this fantastic presentation. I'm looking forward to see Huber in our panel where we talk generally about AI. That was a perfect introduction for the panel, so thank you so much and good luck for the rest of the day and of course for the progress in your initiative. Thank you so much.
Thank you very much for the opportunity, and I would also like to thank my team and everybody contributing to this wonderful, interesting project.
Very good. Thank you so much, Andreas. So, ladies and gentlemen, that was really a deep talk about AI, and I really appreciated that. And please stay tuned. You will enjoy now a few highlights of the Formnext to get even more impressions. And after that, we step into our panel about AI, and I'm pretty sure you will stay tuned. So, see you in a few minutes.